A, Z. So this will be A minus 4, Z minus 2. And there is energy. Then beta emission. This is A, this is Y, Z plus 1. And there is energy. And then for gamma, so this will again be just A because there is no change, and this is gamma. Okay, so based on that, there are some questions. So I'll first write down the question, allow you to think, and then you can complete the question. So let's take the first question where there are numbers given to you, and then we will complete it. So this is 214, and this is X, and this is 85. It is giving out an alpha and turning into a x1, which is giving out a gamma and turning into a x2, which in turns give out a beta and turning into a x3, which in turn is giving out an alpha and turning into x4. Okay, so I would like you to write it down in a notebook and try to answer this. Now, for this one, alpha is given out. So 214 will be reduced by 4. So it will become 210. 85 will be reduced by 2. So that will become 83. When gamma is given out, there is no change. So this is 210 and 83. When beta is given out, we know that this is incremented by 1. So this becomes 84 and this is 210. And again, when an alpha is given out, so that will be 206 and this will be 82. So this is how this equation is completed. Okay, did you understand that?
Yes, sir. But is there any specific workings that we have to show for this?
No. So this is the question. You have to write the question and fill up the blanks. So there is no working required in this.
So this can be asked as an MCQ also, right?
In an MCQ, there will be only one blank or something, or two blanks. Okay, not like these many blanks.
Okay, sir.
So suppose they ask you only this, and they give you option like 210 and 83 as option A. So 210 and 82 as option B. That way. So you have to select the correct option.
Yes, sir. But is there a chance that they can ask a question like if they're given already 214 and 85 gives to 210 and 83 asking at which radiation is emitted? Can they ask it like that?
That also is a question. Good.
Okay,
Okay.
sir.
Yeah. So now this is a question. So there is A and Z, and it says that it emits 2 alpha particle and 1 beta particle. Okay, and it turns into 222 and 85, and it turns into radon. So the question is, find A and Z.
So my bad, 230.
Yeah. So when you have A and Z, and say I'm writing it as one equation, or let us write it one at a time, 2 alpha, it will turn into say x1, and you will have A minus 8 and Z minus 4. And then when you give out a beta, it becomes x2. So this is A minus 8 and Z minus 3, because it is Z minus 4 plus 1. So it is becoming Z minus 3. So now we know that this is A minus 8 and Z minus 3 is same as 222R and 85. So therefore I get A minus 8 is 222. So A is equal to 230 and Z minus 3 is equal to 85. So Z is equal to 88. So that's the answer. A is equal to 230 and Z is equal to 88. Okay. Now in this question, which is different from the one we have done earlier, we have to work things backward. So what will be the value of A and Z after alpha is given out? A turns into 72.
Yeah, so A will be 180, right?
No, it will be 176 because 176
sorry. Yeah,
yeah,
not double.
is reduced by 4. And same with Z. So it should be 71, right? 71 minus 2 will give you 69.
Okay, correct.
Yeah. Okay, so what do you think will come over here then?
So over there, it should be 180
Yes, 180 is correct.
and 73.
Very good. Okay, now what about this? Beta is given out.
184.
So remember, when a beta is given out, A remains A, and this becomes Z plus
Oh,
1.
sorry. Yeah. It's beta. 180 and 74.
It will be 72. Yeah, so that will become 73, right? So these are the type of questions which are expected in this, where there will be some equation given to you, and you have to fill the remaining. Okay. Next, what we are going to see is properties of alpha, beta, and gamma. So first, I will tell you what is the nature. Okay. Nature means what is alpha. We have already discussed that alpha particle is nothing but a helium nuclei. Okay. So therefore, it is positive, and the charge on the alpha particle will be 2 times 1.6 into 10 to the power minus 19. So the charge will be 3.2 into 10 to the power minus 19 coulomb. So that is the charge on an alpha particle. Okay, it is a helium nuclei. Then what about beta? So beta is nothing but an electron. So whatever characteristic the electron has, beta also has. So the charge on beta is negative 1.6 into 10 to the power minus 19 coulomb. Then what is gamma? Gamma, as I told you, is electromagnetic wave. So this is energy, and it has no charge. Okay, electromagnetic waves have no charge. Fine. So if they have charge, alpha and beta, then they will be affected by electric field and magnetic field. So how do we demonstrate that? So these are the diagrams which will also be asked. So this is a positive plate, and this is a negative plate. And here what we have is a lead box. So this thing is lead, which absorbs radiation, and there will be radioactive substance placed over here. So from this radioactive substance, alpha, beta, gamma is being emitted. So gamma goes straight, it has no charge, so it will not get affected. Beta is negative, so beta will get pulled toward the positive. Gamma is positive, alpha is positive, therefore it will go toward the negative plate. So this is alpha, this is beta. So this is a very simple diagram. In this diagram, you have to note that beta particle is negative, and that's why it goes toward the positive plate. Alpha particle is positive, therefore it goes toward the negative plate. However, I have drawn beta particle deflecting much more than alpha particle. So alpha particle goes ahead and deflect, whereas beta immediately deflects. The reason for this is beta has negligible mass. Okay, here you can see that alpha has more charge than beta, but still alpha deflects less because alpha is very heavy. Okay, it is much, much heavier than beta. And that is the reason why alpha is deflected this way. So while you're drawing the diagram, if you draw alpha also same as beta, that will be given wrong. So you need to be careful about that. Okay, there will be questions that they will ask. So they can give you like 1, 2, 3, and ask you to identify which one is 1, which one is 2, and so on. Okay, so you need to be careful that this is positive. So if they change the diagram, okay, like, and they make this as positive and this as negative, okay, and they'll just draw this. So again, you should be able to identify that this is a negative plate, so this has to be alpha, and this has to be beta. Okay, so this is about electric field. Now I will show you about magnetic
Sir,
field.
I had one doubt.
Yeah.
So for basically alpha, you said that beta has negligible mass. So it is
Yes.
alpha's mass that is actually helping it to go up. And for
Yeah.
gamma, is there, how is it like still like without any charge? So is gamma massless?
Yeah. Electromagnetic wave, it is energy. It has zero mass. Okay, zero rest mass. Alpha is heaviest. Beta is after alpha, and gamma, of course, has zero mass. You are not expected to learn the values of the mass of alpha, beta, gamma, but definitely you should know the this thing. You should know the charge. Okay, so that is required. Now, what do you see over here? This is magnetic field. Now, crosses. Okay, cross indicates what? So cross indicates that the field is perpendicular and pointing inside. Okay, so the crosses indicate the field is going inside. So remember one thing, like an arrow. If an arrow is shot, so what you see at the back of the arrow is a cross. And when the arrow is coming towards you, you see a point. Okay. So a cross indicates moving inside the page. So when the magnetic field is directed perpendicular to the page pointing inside, and then you are shooting alpha, beta, gamma, how will they deflect? So what you need to remember over here, sorry, is this: alpha particle will always deflect to the left. So alpha will deflect to the left, beta will deflect to the right, and gamma will deflect straight. So you need to remember the direction of deflection for alpha, beta, and gamma. Okay, alpha
So,
deflects to
so
the,
even
yeah,
in the electrical field also, will it always be that the negative sign will be on the left?
no. So that's what
Because
I
it's going
told
on the.
you. I drew it and I changed it also. So when you make this negative, so you will have alpha coming there. Okay, and this will be positive. So you will have beta going there. Okay, but now suppose, for example, you want to change the direction of the magnetic field. So this is denoted this way. So there are these dots. So the dot indicate that the magnetic field is perpendicular to the screen coming out of the screen. So that is how the magnetic field is. It is perpendicular to the screen coming out of the screen. Fine. So now in this particular case, alpha will deflect to the right side and beta will deflect to the left. And gamma, of course, goes undeviated. So these are the diagrams that is with respect to the electric and magnetic field that you are expected to know. Okay. Then what we have is the next property for alpha, beta, gamma is ionizing power. So for ionizing power, okay, alpha ionizes most, then you have beta, then you have gamma. By ionizing, it means lodging of electrons from the atoms and molecules of air. So when alpha particle is traveling in air, it collides with the atoms and molecules of the air and ionizes them. That means it removes an electron or two from the atom and molecule. So alpha particle ionizes most, then beta, then gamma. The kind of question expected is to arrange them in the ascending order or the descending order. The next property is penetrating power. Okay, so if you have something like this, if something traveling on one side is able to come out from the other side, that means it has penetrated. So penetrating power is again, alpha is the least, then you have beta, and then you have gamma. So gamma can travel, few hundred meters in air. It can pass through metal sheets, concrete walls. But beta on the other side can travel few meters in air, whereas alpha particle travels only, 3 to 8 centimeters in air. So that means these alpha particles, which have been given out by the radioactive nuclei, can only travel some distance up to 8 centimeters. Okay, whereas gamma can travel like kilometer. So gamma can travel pretty far. Okay.
So
After, yeah.
basically, in alpha, the moment it's emitted, it
Mhm.
stops at a particular point. So that's the end of the magnetic field.
No, that's the end of alpha. Alpha being
Okay.
absorbed. Like for
Mhm.
example, if you have a shot put ball, you throw the shot put ball, it can travel only a certain distance. But when you have a cricket ball or a tennis ball, if you throw it, it does go far. So alpha is pretty heavy, and therefore it loses energy because it tends to collide with the atoms and molecule, and it is absorbed. So alpha doesn't travel far. So imagine if there is a radioactive substance, even in some place, it is definitely not going to damage anything away from it at a distance from it. But gamma can definitely damage. Okay. So the next point of comparison is stopping substance. What can stop alpha particle? So human skin, thin paper sheet can stop alpha particle. Whereas beta particle, you require a millimeter thick lead sheet or say 5 millimeter thick aluminum sheet. So if you have a cavity, like this is good enough to stop alpha and beta both. Okay, but for gamma, you require some centimeter thick lead. Okay, if it is iron sheet, it requires 30 centimeter thick iron sheet for it to stop gamma radiation from going on the other side, and few meter thick concrete walls. Okay, so the metro pillars, that they are a couple of meters thick. So alpha particle can pass through them as well. Okay, and that is the reason why the nuclear reactors are built in a way that they have few meter thick concrete walls. They have steel walls also in between, so they tend to be shielded so that no radiation escapes out. So this is the stopping substance that you are expected to know. And the last point of comparison is biological damage. So obviously, gamma is known to cause immense damage, alpha being the least, and beta is between alpha and gamma. So everything is either this way or it is either this way, and mostly it is comparison. Okay, like the penetrating power I mentioned, gamma has the highest penetrating power. It can penetrate through sheets, a few meter thick concrete wall and 30 centimeter thick iron sheets as well. Okay, any questions so far?
No, sir.
Yeah. Next is a lot of theory again. First is medicinal use. In medicinal use, you have now remember, in all these uses, you have to give example plus name of the isotope. So like medicinal use, you have to say that it is used for the cure of leukemia, cancer, and the radiation of cobalt-60 is used. So just writing it is help to cure cancer will not give you marks. You have to write cobalt-60 as well. Then the radioisotope of sodium chloride, iron, iodine is used for diagnosis. They are used as tracers. Okay, so the person who is undergoing treatment, his body is injected with a fluid which have these isotopes, and these isotopes go and get mixed in the blood, and they go around the body, and they are detected by the CT scan and all. So they know where the problem is. So tumors can be detected like that. Okay, going ahead to industrial use, we know that radioactive isotopes are used to generate electricity. So they are used as fuel. Then they are also used, okay, like illuminescent, you have the glow sign or the ice cream parlor and all. So their radioactive isotopes are also used. Then there are many other things like the beta radiations are used to control the thickness of the paper. So from the pulp of the paper, when paper is made, to determine the thickness, beta particle is given out. So when beta particle goes to the other side, and if the paper is of certain thickness, then the intensity of beta particle going out will be different, and thus you can determine the size of the paper. Also talking about scientific use, so alpha particle is used to use as a projectile in nuclear reactions. Okay, so alpha particle, there is a phenomena called as scattering that is used to determine the size of the nucleus. So when alpha particle is going toward the nucleus, it gets deflected. It goes toward directly, it will go back. So when it is traveling away, the deflection will be less. So therefore, you can determine the size of the nucleus using alpha particles. Also, if you have heard about, there are ways in which the age of the fossils can be determined. So that is used by a radioactive isotope of carbon, carbon-14. So that is used for a process to determine the age of the fossil, and that is called as carbon dating. So I repeat again, along with the uses of radioactive isotope, you have to write the name of the isotope as well. Okay, moving to the next. Here, there are certain things which I will go back to the previous slide. Now, in sources of harmful radiation, there are three sources in this. Number one is of a nuclear power plant accident, if there is a radioactive fallout. So if there is a radioactive fallout, then basically there is an accident at the site of the nuclear power plant. then there is a lot of radiation that is given out in the atmosphere. So that is one of the source of harmful radiation. Okay, there are examples which you must be aware about, like there is Chernobyl, okay, which was in Ukraine. Then there is one which happened in Japan. There was a earthquake and tsunami which caused the radioactive, the nuclear reactor basically to get damaged, and therefore a lot of radiation was given out. So that is one source of radiation. The second source of radiation is nuclear waste. Nuclear waste is generated from radioactive nuclear power plant. It is also generated from hospitals where radioactive isotopes are used, because after use they continue to remain radioactive. Okay, one thing that you need to know, that for thousands of years they remain radioactive. So after they are used, you can't just dump them like garbage. They need to be taken care of. Otherwise, they are also the source of radiation. And the third source of radiation is cosmic radiation. That means radiations from outer source, outer space. So there are some radiation which enter the atmosphere and reach the surface of Earth. Also, there are these X-ray generators. So they are also the source of harmful radiation. Okay, any questions you have?
So basically, for like in atom bombs also, are there like radiations that come out?
Yeah, definitely. So, like suppose there is a nuclear attack. So after the nuclear attack, also the radiation remains. So like Hiroshima, Nagasaki, that Oppenheimer is all about. So the bomb exploded, that destroyed building, that killed people. But unlike other bombs, this bomb contaminates the air, contaminates the soil, and that radiation remains. So the people who survive are also exposed to that radiation, and they are affected. Okay, so that's also a source of radiation. Next, you have the safety precautions while using nuclear energy. Okay, so before that, these harmful radiation, they have some effects also. So those effects are also categorized as short-term effect, which are recoverable, like hair loss, nausea, diarrhea. There are long-term irrecoverable effect like cancer, leukemia, and the third is genetic effect. So the people like you just asked, those who have survived the nuclear blast, nuclear bomb, they have genetic mutation because of the high exposure to these radiation. Now, when these people give birth to young ones, kids, those kids are born with deformities. So not only in humans, but animals which are exposed to the radiation, when these animals give birth to young ones, they are born with deformities. So these are short-term recoverable effect, long-term irrecoverable effect, and then genetic effect. So these are the harmful effect of radiation. Then safety precaution. Now safety precaution again is categorized into one. When you're talking about safety of an individual, so you wear lead line aprons. While handling the instrument, you're using lead tongs. So that is about personal safety. The second is safety of the nuclear power plant. So you build a nuclear power plant away from human settlements. You build a nuclear plant which is an area which is not earthquake prone. You should build a nuclear plant which is earthquake resistance. Make sure that it is strong enough that it can withstand the earthquake. So these are the precautions. And the third precaution is of the waste, nuclear waste. Now this question has been asked multiple times in the board exam also. So you have to keep the nuclear waste into lead boxes. Okay, so this is lead box. And then you have to keep these lead boxes into old unused mines, or you have to keep them into deep ocean. So both these steps together give you that mark. So keep the nuclear waste into lead box, and then keep the lead box into old unused mines, or keep it deep in the ocean. So these are the precautions for individual, for the nuclear power plant, and how to handle radioactive waste. And the last part is about background radiation. So background means what? Something that is there at the back, but it is not affecting us. Okay. So these radiations are there in the atmosphere, radioactive radiation, but because they are small in intensity, they don't affect us. They are categorized as internal, which are given by carbon, potassium 40, carbon 14, and there are external sources which are coming out from the space, cosmic rays, and so on. So this background radiation also is a 2-mark question. okay, which is internal source and external source. Both you need to know the examples of. Okay, so now what we are going to study about is nuclear fission. By the word itself, it understands that it is breaking something. Okay, so this is one example. This is uranium, and this is a neutron. So a neutron which is moving, it gets into the uranium nuclei, and then it splits the uranium nuclei into two. So this is barium and this is krypton. Plus, it also gives three other neutrons. Okay, so this is the fission reaction. If you want to write this reaction, how will you represent it like a chemical reaction? So uranium and one neutron, okay, that gives rise to 236 and 92. That is like a temporary thing. And after that, it splits into barium and krypton, okay, which is approximately like there are two parts equal. So this is 36, and there are three neutron, and this is energy. Okay. Now this energy is important because for one fission reaction, it releases around 190 mega electron volt. You need to know only that. Okay. So one uranium nuclei, when it splits, it gives that much energy. Okay. And you should know where this energy is coming from. So this energy comes from here. So you can see this is an arrow. So before that, these are the reactants. So let's say these reactants have mass M1, and these are the products. So these products have mass M2. It is observed that the reactant's mass is more than the product's mass, and therefore the difference in mass, that is M1 minus M2, which is equal to delta M. Now delta M changes to energy. Okay, now we know the formula, that is E is equal to mc squared, where M stands for mass, C stands for speed of light. So E equal to mc squared is this difference of mass is what is getting converted to energy. So this is very important. Okay, for I mean that much you need to remember. Of course, you should remember the equation. You should know that one nuclear fission of uranium gives 190 mega electron volt. And why? Because the difference of mass is getting converted to energy. Do you have any questions?
No, sir.
Okay, so I'm going to try and make you understand one more fact, that 190 mega electron volt. So mega is 10 to the power 6, and electron volt we have done in the work energy power chapter is 1.6 into 10 to the power minus 19 joules. Okay, so whatever answer you get for this is 10 to the power minus 13. And even if you say that it is like, this is around 300 or so. So approximately also if I say 300, that is 10 to the power minus 11 joules. So this is pretty small. Okay. So this is less energy. 10 to the power minus 11 joule is small. Okay. But remember, this is only one nuclei. So if you take a gram of uranium, there will be many nuclei in that 1 gram. And therefore these 1 gram, it is said that it can give energy, which is around 2.1 into 10 to the power 4 kilowatt hour, which is also equivalent to 20 ton of TNT. Now, TNT is an explosive. So the explosion that will 20 tons of TNT cause, that much energy can be given by just 1 gram of uranium. So that's pretty massive. You don't need to know all this information. Okay, you just need to know what I told you over here, right? Okay. Now, before we move ahead, another point I would like to make is the following. So you have one nuclei fissioned that give you three neutrons. Now imagine these three neutrons will fission three other uranium nuclei, and each one of them will give you three more neutrons. And those three will in turn fission like these 9 uranium, which will give you 27. And if this continues, within no time, all the uranium available will get fissioned, and therefore the amount of energy given out will be enormous. This is called as chain reaction. Do you understand the meaning why it is called as chain reaction?
Yes, sir.
Okay, because 1 gives out 3, 3 gives out 9, 9 gives out 27. So this is what happens in nuclear bomb. Okay, a nuclear fission bomb will somehow try to fission one uranium, and then it will give out more neutrons, and it will have enough uranium so that these neutrons can hit uranium nuclei and give out more neutrons and give out do more fission. Okay, so this is not an ideal thing, and that is the reason why in a nuclear reactor, which what we have is called as controlled reaction. Now, in a controlled reaction, there are certain rods of material, okay, which absorbs the neutron. And because they absorb neutrons, okay, they can control the number of neutrons available. And what they do is they control the rate of reaction. And these rods are cadmium rods, okay. So they are the one which absorb these absorb the neutrons, and they control the rate of the reaction. Okay, so in a nuclear power plant, these are there. So you need to know a little bit about them. Okay, and the last thing is use. What is the use of nuclear fission? Obviously, the first use is to power generation. So all the nuclear power plant, they use fission. And of course, the other use is destructive, where the nuclear bombs are used, okay, which is also called as an atom bomb. Okay, so they are the one which are using nuclear fission. Any questions you have?
No, sir.
Okay, so if you are asked to distinguish between radioactivity, which we studied in the A exercise, and nuclear fission, the difference will be radioactivity, as we discussed in the previous exercise, is spontaneous. You cannot control it, you cannot predict it. But nuclear fission is controlled because you initiate it with the help of neutrons. So if you don't fire the neutrons, you will not get the nuclear fission. Okay, and new radioactive decay, alpha, beta, gamma is given out. In nuclear fission, a nucleus breaks into two, and it gives out uranium, and it gives out energy. So the energy given out is high in nuclear fission. Even the rate of radioactivity cannot be controlled. As I told you in the previous exercise, alpha is given out, beta is given out, gamma is given out. You cannot control which is given out when. But in a nuclear fission, you can definitely control the reaction. Okay, moving to the next is nuclear fusion. So this is nuclear fusion. So what is fusion? Coming together. So you have one nuclei, you have another nuclei, they come and become one, and energy is given out. So where do you get this energy from? As I told you, we call this M1. This is M2. Again, M1 is heavier than M2. So M1 minus M2, which gives rise to difference of mass, which give rise to energy. Okay, so that is E is equal to mc squared over here. Again, there is an example which you are expected to learn. So this is a single example. So you have hydrogen, that is deuterium, isotope of hydrogen. It combines to give you a helium isotope, and one neutron is given out, and 3.3 mega electron volt of energy. Now this helium isotope in turn absorbs another hydrogen, and it becomes a helium atom, and it gives out a proton, plus it gives out 18.3 mega electron volt. That means a total of 21.6 mega electron volt of energy is given out. So this is one example of nuclear fusion, which you need to learn. There are other examples also given. You are expected to know at least one. Now this is called as a thermonuclear reaction because This reaction requires very high temperature and very high pressure. Okay, so very high temperature, very high pressure is required for nuclear fusion. It cannot happen at ordinary temperature and pressure. Okay, so that is what happens on the stars where the nuclear fusion happens, and that is where the star get the energy. Also, the destructive weapon like a hydrogen bomb. So hydrogen bomb uses these reaction and gives a lot of energy. Of course, 21.6 mega electron volt is less compared to 190 mega electron volt of one uranium nuclei. But if you have equal mass of uranium and equal mass of hydrogen, then the number of atoms of hydrogen in that will be much greater. And therefore, there will be more fusion reaction taking place, which will in turn give rise to a lot of energy. So in a hydrogen bomb, they first do fission. Now fission give rise to the high temperature and pressure, and then fusion happens. So in a hydrogen bomb, there is fission and then there is fusion. Okay, so both are used in that. And you can pack in as much of hydrogen that will cause more and more damage. Then what is after this is the difference between fission and fusion. Okay, so in a nuclear fission, there is a neutron that breaks a heavy nuclei into two and gives out energy, and a nuclear fusion, two lighter nuclei combine together to form one heavy nucleus. Okay, so this reaction of nuclear fission can take place at ordinary temperature and pressure. Nuclear fusion takes a lot of temperature and pressure, very high temperature and pressure. One fission reaction gives around 190 mega electron volt, whereas nuclear fusion gives around 21.6 mega electron volts. Okay, so at least these points of difference are there. Okay, plus the exercise that I have shared in the notes, you can solve those questions. So this is the end of this chapter. Do you have any questions?
No, sir.